Okay, go ahead and get this ready here. So what I looked at was how can we use remote sensing applications to predict the risk of wildfire severity in Northern California. And by severity, I mean that's the amount of acres that are burned on land. So in this study, one of the things that every emergency management response agency is going to face is going to be getting your response resources to the point of the emergency as quickly as possible. Now, in Northern California, there are two wildfire agencies that we're looking at. There's, of course, the United States Forest Service, and then there's CAL FIRE, and that's CAL FIRE's, and CAL FIRE is sort of California's own state forest service. They're also in charge of forest management and suppressing and managing wildfires, but they just do so on state lands and private property. So in order to assess the risk of large wildfires in Northern California, I'm going to be taking a look at three variables. I'm going to try to be looking at the vegetation type and species that's occurring in the fire shed. I'm going to be measuring how dry the fuel is. If fuel is not dry, it will not ignite and it will not burn. And to create a metric to measure the density of the fuel, the amount of fuel that's available for a wildfire to consume and spread. And in the end, I'm going to take these three variables and I'm going to be regressing them against actual wildfire data for the study area from the year 2002 and see if indeed these metrics that we've created are reliable predictors of wildfire. So, and our study area is, as I said before, we're looking at Northern California, and particularly we're looking at the counties that are within, I believe, Path 45, Row 32 of Landsat 7. So that includes the vast majority of Shasta County and a bit of the eastern portion of Trinity County and a sliver of Tehama County to the south. Now, the study area has many types of vegetation occurring within it. As you can see in kind of the south-central portion of the study area, this area where you see a lot of brown, white, and white. This area is the California Central Valley. This just sort of snakes through all of Central California, and this is kind of the northernmost point. This includes, and then towards the center of the valley, vast fields of agriculture, some urban centers, and as you go away, you start to hit the Central Valley foothills, where you're starting to see annual grasslands. At the very top is where two great mountain ranges of California converge. To the east, mostly in Shasta County here, you're seeing the California Sierra Nevadas, and to the west, and mostly in Trinity, you're seeing the California Klamath Mountains. And both of these have vast forests of ponderosa pine, Douglas firs, and different conifer species that are native to each mountain range that I mentioned. And all in all, the study area amounts to about 6.8 million square miles in area. And I'm going to attempt to develop these variables to estimate wildfire for the entire area. Now, for the first one, our first estimate is going to be fuel dryness. Moist vegetation or fuel will not ignite, or generally not ignite, or not burn as quickly, and therefore less severe wildfires. So to do this, I used solar insolation. So to my benefit in ArcMap, there is a solar radiation area tool, and this I use to calculate solar insolation between 11:55 a.m. and 12:05 p.m. on July 15th, 2002. That's when all my rasters were taken. It was the best clear day I could find with the minimum amount of banding. So sort of about 5 minutes before the sun would hit its zenith, and about 5 minutes after it would hit its zenith. So as you look at the area, usually in the south forward-facing mountain slopes of the Klamath, to the west, the Sierra in the east, we're seeing the most solar insolation. And solar insolation is twofold. Not only does it measure dryness, it can also measure vegetation growth, because the climate of Northern California is a Mediterranean climate. By that, I mean we're talking about very wet winters where it's very overcast, it drizzles and rains very frequently, and then by hot, dry summers. And this is when the majority of wildfires occur. So lots of solar insolation during rainy period, you're going to see vegetation build up, and then during the hot, dry period, the increased solar insolation will then dry that vegetation out at a quicker rate. Now, our second variable that I also included, these are kind of meant to complement solar insolation because solar insolation does not explain both vegetation growth and increase in biomass or fuel, and then that drying out and becoming a potential fire hazard. So I used two vegetation indices to do this. One is just an NDVI, which is just measuring the difference between band 3 and band 4, and what would be called an NDVI for foliar moisture. Now this uses band 4 and band 5 difference to focus more on plant moisture. Now the NDVI I included because solar insolation alone does not explain, say, plants increases in biomass. So because different plants, let's just say the montane charapel or blue oak, are going to respond differently to how they grow with increased solar insolation. So NDVI was kind of included to create another parameter for vegetation biomass, and the foliar moisture NDVI I included because, well, solar insolation is not going to take into account precipitation, which of course is not going to be uniform across the fireshed, and of course different plant species are going to be able to hold on are going to have different plant moistures. Even during the hot summer months, some plants are much better at retaining their fuel moisture, and also because precipitation across the study area is not going to be consistent. So I included this metric as well to look at the moisture of the soil and moisture of the vegetation within the study area, as it goes without saying, of course, plants that have a lot of fuel moisture are going to be less susceptible to wildfire ignition and spread. And if we just take a look at these, are just the same study area, but with these two NDVIs laid under them. So if we look at our foliar moisture, we're seeing that the areas that would be the foothills of Central Valley, kind of along the border of Tehama and Shasta County, those areas are representing the more kind of dry areas, and perhaps a little more dry areas up in the northwest extremity of the study area, and the rest is we're seeing pretty high amounts of fuel moisture, especially in the Sierras over in the eastern portion right here. Now, for the vegetation index, just our normal NDVI, we're seeing kind of a similar pattern played out with very heavy amounts of vegetation in these mountainous areas here, and then more sparse towards the Central Valley itself. And those are going to be the two variables, one of vegetation biomass and moisture, and the other of solar insolation and dryness. Now, our third one, it took a good amount of work to get to. This was our vegetation classification. And so an individual species of vegetation can have a pretty significant impact on wildfire behavior. Let's say if we're looking at annual grasslands or blue oak, they might be susceptible to frequent wildfire, but they're going to just be extinguished pretty quickly and not be much concern. Now, if we're looking at, say, ponderosa pine or montane chaparral or something of that nature, those are going to be very susceptible to wildfire and create these large infernos. So the classification method I'm using, I'm actually borrowing a lot of steps from the article describing the brush fire hazard in Southern California, which has about four authors, and one of them is actually the University of Arizona's own Dr. Stephen Newell. And okay, so I'm testing two different band combinations here. One, I'm following the article I mentioned before. This is using band 4, 5, 6, and 7. It's including the thermal band here, which might seem kind of odd, but the thermal band can be used to look at heat stress in plants, which might be indicative of a potential wildfire. And another one I'm using bands 4, 5, and 1. And on both of these, you can see sort of the reddish areas are areas of high vegetation, and as we get to the Central Valley, we see there's these either aquamarine or teal colors emerging, which are representing sort of our grasslands, our montane hardwoods, and other sort of foothill vegetation. Now, for each of these two band combinations, there were three separate classification methods that were used. One being supervised, where you dictate the your test sites, and from data that you know or data that you have, and then of course unsupervised ISO classification, and from that also maximum likely classification. And the goal here was just to find which band combination and which classification method is going to be the most accurate. And that one, when I go on to my regressions and test these variables against actual wildfire data, which of these are going to be the most accurate, and that one I'm going to use as a variable in the regression instead of just regressing all of these at once. There we go. Okay, so for supervised vegetation classification, I was fortunate enough to have a vector feature class that outlined the vegetation within CAL FIRE's, the state wildfire agency's protection areas or areas that are responsible to respond to wildfire in for a good portion of Shasta County. And I used this as the basis for my training sites. Now, there were about 15 types of vegetation within this vector of vegetation, and a couple of them I clustered down into one classification if they were just spectrally very similar or really similar species. For example, we have our blue oak, foothill pines, and foothill oaks. Those were actually very similar. They were combined into one. We had conifer, montane mix hardwood. Those were clustered down to one. And then our montane chaparral and Chinese chaparral were clustered down to one. So all in all, we had 12 vegetation classifications. And I note that I also included agriculture and water, lakes, bodies of fresh water in the study area, and urban areas. Even though these aren't really wildlands, a fire that breaks out in an urban area is not going to be considered a wildfire by any means, but they were included so that the classification schemes could differentiate what is wildland and what is going to be non-wildland areas, because there's frequent amounts of agriculture, especially in the southern part of Shasta County, Tehama County, some parts of Trinity, and large urban areas that dot the study area. So using 12 classifications, and for the unsupervised classes of most likelihood and unsupervised ISO, we used 12 classifications as well. For our classification groups, I've included here. This count accounts for 98% of the vegetation that we're seeing in this polygon right here. So after running supervised classification, creating 10 training sites for each of these 12 vegetation classes, and specifying for our unsupervised classifications use 12 classes. These are the results that I came up with for each of the classifications for each band combination. Not the greatest and least, but if I found anything from this, when I ran the classifications, and tested them with accuracy points, we had a lot of the different conifers. Like we have conifer trees for the Sierra Mountain Range, another for the Klamath. We have Douglas firs. We have ponderosa pines. That was the most biggest contributor to having our accuracies thrown off, was just getting essentially various pine trees mixed up with each other. And interestingly enough, another major source of error was agriculture, mixing up, say, annual grasslands or even blue oak forests for agricultural fields. So when I move to test these variables, now I'm going to be selecting using the classifications from my band that uses my combination uses bands 4, 5, and 1 supervised classification. Okay, so now just moving on to our empirical testing. How do our variables affect wildfire? Are they significant explanatory variables? Going to be using 308 wildfires, which from the year 2002, and we were looking about an average for each wildfire. The average burned acres is around 3.5 acres, usually lasting no more than about 3 hours or so. As you can see from the image right here, a lot of CAL fires, areas are fires in the Central Valley, The U.S. Forest Service are up in the Sierra and the Klamath Mountains. So I'm also going to be including a dummy variable, to indicate which wildfire management agency is fighting that fire, just to see and make sure and test and control for any variables between CAL FIRE and the Forest Service, how they may approach wildfires. Perhaps CAL FIRE has a structure that allows them to respond faster versus the Forest Service, and I'd like to control for that factor. Okay, so I'm sure you're wondering how I'm going to be quantifying these vegetation types to test them against wildfires. So I created dummy variables for the vegetation, as each has what's called a fire regime. Both the U.S. Forest Service, CAL FIRE, Bureau of Land Management, they all use the same methodology of classifying vegetation into a fire regime. This is just a nominal number. It's assigned to vegetation that designates its frequency and severity. It goes 1 through 5. In our original CAL FIRE protection areas in Shasta County, the vector file that I was given to use for my supervised classifications, we only have regime 1 and regime 3 in the study area. So regime 1 includes grasslands, montane and foothill hardwood, blue oak forest, many different types of small conifers, and the Klamath conifer and the Sierra conifer. And they are very frequent wildfires, but they often burn themselves out very quickly. So often by the time that the response arrives to the ignition point, the wildfire has burnt itself out. And regime 3, these are the ones we kind of want to worry about. These happen less frequently, but they're happening in the areas of Ponderosa and Nixon, Montane, Chaparral, that we're seeing these large infernos that spread very quickly. They're very high severity. They tend to burn hundreds of acres at a time when they're left unchecked. So I created dummies for whether the vegetation was regime 1 or regime 3, or if it was urban or, say, agriculture or water, it was given a dummy of no regime. Okay, so in order to test this, I used just ordinary least squares regression, and I was using wildfire severity, in the sense the number of acres burned when the fire reaches maximum size, as a dependent variable. And we were using solar insolation, our 2 vegetation indices, and our classification dummy variables, and our dummy variable for wildfire agency. And I also included a few interaction variables between solar insolation and our vegetation indices, just to see if that would create a more significant explanatory variable on that end. So here's my regression results. Now, the most significant finding is that our dummy variables for regime 3, that's the less frequent but very severe regime, was found to be significantly significant. And let's just say the marginal increase for that is we're going to see an additional 16 to maybe 18 acres burned. And for regime 1, we're looking at also found to be significant with about maybe 14, 15 acres burned. Now, our vegetation indices and our solar insolation, I didn't find them to be significant, but on the bright side, they did, their coefficients were in the direction I would assume. So solar insolation increasing, solar moisture decreasing, and biomass and DVI is going to be increasing wildfire. And luckily, I've also found that the institutional effects, the wildfire agency dummy, that was not found to be significant at all. Okay, so in conclusion, I believe that these 3 variables and these systems, purely using remote sensing, did not have to go out into the field and sample anything, are effective method to determine wildfire size. While a number of the variables were not found to be significant, their parameters did take the expected sign. And I think there's a lot of potential for future research. Let's just say if we want to use larger sample sizes, we want to use more recent data, and I would like to eventually maybe make this take a look at maybe just wildfire risk, maybe by using by each fire, looking at the number of fires in each fire district and using the same dependent variables, but maybe using something that would estimate risk, like a probit or a poison, or most likely a destination model. And that's that for me.